Dear students, back again to Tautomerism. After the episode 1, our teacher Nur Haq enters to episode 2 of Tautomerism with more and more precise, specific, and practical examples. He deals with phenomena like why one alpha hydrogen prompts to form double bond with nitrogen to form groups with oxygen, certain how new groups like oximes are formed, why oximes are more stable than nitriles. He deals with multiple such issues. So let's go ahead.
Dear students, as you know, we are still cultivating the concept of tautomerism, and also I have given so many examples. Let's roll further and break the mystery. I'll give more example on tautomerism, specific and rare example. In the first part of tautomerism class, I have discussed only the keto and enol tautomerism, but another system may show also tautomerism. That means it's a different tautomeric form you may get. See, it is a nitrosyl compound. NO group is called nitrosyl. HXY double bond Z. This skeleton structure is the basic structure of tautomerism to show the tautomerism. Now here this is alpha hydrogen. This will make double bond with nitrogen and it goes to form bond with oxygen. Give reversible sign, what you will get? RCH double bond NOH. Can anyone tell me, after tautomerism you got a structure, it is a new functional group, and you know the name of the new functional group is oxime. Oxime. And remember, this is keto-like form and double bond O form. This is oxime form, and you know this, if R and H are different, then it will show geometrical isomers, seen and NT. And surprisingly, here oxime more stable than nitrosyl form, and this one major always. It has major contribution than nitrosyl contribution. Minor, remember it. That means any nitrosyl compound, if there is alpha hydrogen, it will participate in tautomerism. It will participate in tautomerism. Nitrosyl compound will give oxime structure. Now, another structural form, that is nitro compound. You know the nitro compound structure. This is plus, this is minus. You can take coordinate bond arrow or plus minus. Here it is alpha hydrogen. This is also tautomerism, and you will get this form. RCH double bond N, single bond OH, and this is O minus, this is plus. This hydrogen can make bond with this oxygen also. That's why these both nitrogen oxygen bond lengths are equal. And this tautomeric form reduces the carbon nitrogen bond length. Here also reduces the carbon nitrogen bond length. That means other than keto-enol tautomerism, I have given here two different examples. One is nitrosyl compound, another is nitro compound. That will also show tautomerism. In nitrile compound, you know, nitrile means C triple bond N. This is C triple bond N. Here minus on nitrogen enough stable to get the real tautomeric form. This will participate in tautomerism, and you will get a new structure, although its contribution is less due to consecutive pi bond C double bond NH. This is the tautomeric form of this structure, but it has contribution, although it is less, which will decreases the carbon-carbon bond length, increases carbon cyanide bond length. Now another system, you can consider this one, any alkyne system. Alkyne, you know, this sp hybridized carbon, this sp hybridized carbon more electronegative than nitrogen. That's why here minus is stable. It can participate to show the different tautomeric form. Condition alpha hydrogen should present, and you will get a new structure which is known structure, that is called allene. Since allene system, you know, in stereochemistry, part we'll discuss alene system. Two pi bonds are mutually perpendicular, and this alene system is the tautomers of alkyne. Remember, tautomers of alkyne. Now, here I'm going to take an important exceptional example of tautomerism. Of course, here keto-enol tautomerism. I'm going to take 1,3-diketone. This is 1,3-diketone, pentane 1,3-diketone. See the structure. Now, this middle hydrogen is highly acidic, you know, due to this two carbonyl group. And its acidic strength, its pKa value near about 9. That is more acidic than phenol. Weak base enough to take this hydrogen. And kinetically this will participate in tautomerism. Thermodynamically also, you know, more substituted double bond, more stable due to more number of hyperconjugation. Now, any one among these two, since two are equivalent, participate in tautomerism. You will get this one. This one. This is the structure. And surprisingly, there you will get a hydrogen bond and you will get a ring. You will get a ring structure, and it has another canonical form. See, right side oxygen may participate in tautomerism. It becomes double bond O. It is OH. This one. And you know, here it is 76% surprisingly in hexane, non-polar solvent. This is 24% in hexane. Whereas it is 13% in water. It is automatically 87% in water. Now the question is, how? In all, percentage is so much abnormally high, 76% in a hexane, and why its percentage reduces with increase of polarity of solvent and it is minimum in water. How? Actually, you have to know what is the reason of additional stability, and due to that additional stability, its percentage abnormally 76%. You know, normally keto form more stable, but abnormally here enol is more stable. You can say, due to hydrogen bond, a 6-membered ring will form. That you know, 6-membered ring stable. Due to that 6-membered ring, it is highly stable, but it is partially correct, not 100% correct. See the magic. Actually, first I am discussing why its percentage decreases with increase of polarity of solvent, and it is minimum in water. Why? Actually, ring for 6-membered ring formation, one of the reason, but the most important reason I will discuss later. If you increase the polarity of the solvent, then this intramolecular hydrogen bond, the intramolecular hydrogen bond efficiency decreases. Why? When the solvent is hexane, say, then this OH and oxygen has no relation with the surrounding. 100% this oxygen focus with this hydrogen to make hydrogen bond. That means hydrogen bond is highly efficient when there are non-polar solvent, when there are zero interaction with the surrounding. I am giving an example. Two students from Bengal or India. In India there was no relation. They go to America to do research. When they will meet, due to cultural similarity, due to language similarity, due to nationality same, they will make friendship. And their friendship is a strong friendship will develop due to weak interaction with the surrounding Americans. But when they will come back to the India, then relation become again weaker due to surrounding interaction, becomes more efficient. Yes, due to similar reason. When the solvent is hexane, then this oxygen, this OH has no relation with the surrounding solvent. They 100% focus with their friendship hydrogen bond. That's why efficient hydrogen bond, efficient ring will form in hexane. But when the solvent is water, this OH and oxygen are involved hydrogen bond with water. So when they involved hydrogen bond with surrounding water, automatically intramolecular hydrogen bond efficiency becomes weaker and ring will not form. Ring is very weak. That's why with percentage of polarity of the solvent, with increase of polarity of the solvent, percentage of enol decreases. Now the question is different. Is only hydrogen bond is responsible, or is only formation of six-membered ring responsible for high percentage 76% in ethanol? It's not correct. See that. If I take another example, see. Ethyl acetate. Here alpha hydrogen. This carbonyl never participate to form enol, since you know there will be a cross conjugation. This is better donor than this non-bonding, high energy, better donor. Sigma bonding, low energy, weak donor. That's why oxygen lone pair gets victory. Net vector there. This is called cross conjugation. That's why this carbonyl never participate. Carbonyl group of ester never participate tautomerism due to this cross conjugation or oxygen donor. In presence of oxygen lone pair, never it will accept the sigma CH bonding. Specifically, this will participate in tautomerism only, and you will get this tautomer. See my structure. This part is ester. Cross conjugation is present here. Here you will get hydrogen bond. But remember, can you tell me, among these two hydrogen bonds, which one more efficient? If electron density on oxygen increases, then efficiency of hydrogen bond increases. O minus will make better hydrogen bond than neutral oxygen, remember. Here electron density on oxygen more, since this OET electron pair donor, which will increase this electron density on oxygen, and this hydrogen bond is more effective than this, if I do consider, or if I focus only that hydrogen bond. But remember, surprisingly, its percentage 7% in hexane. This experimental data will tell you its abnormal stability, abnormal high percentage 76%. Responsible part, not only hydrogen bond, not only this ring. There is another factor which will increases abnormally the stability of this ring. What is that factor? See, this is resonance. Can you tell me how many electrons participate in resonance? You got another canonical form and both have equal stability, both are equivalent. That means this hydrogen bond is not hydrogen bond, 50% hydrogen, 50% sigma. This is 50% hydrogen, 50% sigma. Highly effective. Not only that, 6 electron delocalized ring. You know, 6 electron delocalized ring is aromatic ring like benzene. That means these are aromatic ring. Aromatic ring. Aromatic. The ring has aromatic character due to this conjugation. Remember, this aromatic character of the ring is responsible for high percentage in hexane. But here the ring is not aromatic, although the hydrogen bond is effective. See, why it is not aromatic? This canonical form you can't draw, since in presence of lone pair, never this carbonyl will accept pi bonding. It is lower in energy, lone pair is higher in energy. That's why no conjugated ring. Not conjugated ring. Conjugated ring. That's why its stability is high, abnormal stability due to aromatic character of the ring. Here the ring is non-aromatic. That means hydrogen bond is the driving force to form the ring, but after formation of ring, it will get extra stability due to aromatic character of the ring. That is the responsible for abnormal stability, abnormal high contribution of enol form in hexane. Now, I'll give a chart. These are X and Y. I'll vary this. I'll do vary this X and Y. And I'll do compare the percentage of enol in hexane. X, Y, percentage of enol in hexane. Highly important part of the chemistry. In future, it may come in different competitive exam like JEE Advanced. I have given the specific example when both are methyl. It was 76%. Don't you have to remember the percentage, but the order you have to remember. Now, if I change one methyl by one hydrogen, can you tell me its percentage decreases or increases? For example, I have taken a simple benzene. That ring compare with the benzene. I have taken toluene. One methyl is there. You know one methyl will make three additional hyperconjugative interaction. That will give additional stability. That means here I have withdrawn additional stability by replacing hydrogen. If a stability decreases, then its percentage decreases. Since you know keto-enol tautomerism, totally thermodynamically or stability controlled. The percentage, let it is 53%. I don't know the exact percentage, but it will decreases. That is important. Now if I change both methyl hydrogen, then again it will decreases, let it is 39%. I told you, I am repeating you, that percentage is not important, that decrease is important. Enol percentage in hexane decreases is important, since it is a stability control. Now, if I do replace methyl by phenyl, phenyl you know benzene ring which is itself aromatic, and here I have replaced methyl by phenyl. What it will give? A phenyl ring with a phenyl like benzene ring, you will get resonance interaction between the two aromatic rings, which will give additional stability. Again its percentage increases, and which is more than 76%. Let it is 84%. Now, again I am repeating, this percentage are not exactly same, but very close. The decrease and increase of percentage is important. Now, if I take both are phenyl, then you will get three rings. Two phenyl benzene ring, and that hydrogen bond will form a pseudo-aromatic ring. There you will get so many resonating interaction with that ring, and will give additional stability, and the percentage increases to 96%. Surprisingly. Now, keep this methyl fixed. If I take OET, due to cross conjugation, I have discussed, due to cross conjugation, the ring was not conjugated. The ring was not aromatic. That's why its percentage abnormally less, 7%. If I take amide, CH3NH2, then cross conjugation more prominent, more efficient than OET. Why it is more efficient? Since nitrogen lone pair higher in energy, better donor than lone pair on oxygen. Again, its percentage should decrease, and its percentage near about 4%. This chart will give you idea about the percentage of enol. How enol percentage fall? Only I have explained here, only by considering the stability. Now, solvent effect I have considered here, I have discussed here. In non-polar solvent, effective intramolecular hydrogen bond form effective ring, strong ring, and that strong ring in some examples are highly stable due to aromatic character of the ring. And you got an important idea about the stability of the different tautomers. Now, the chart C, remember. Now, I'll take a ring system. Here I have taken 1,3-diketone. But this 1,3-diketone, if I take in a ring, here, a ring 1,3-diketone. If I do form an enol, remember this thing, don't compare with open chain. This OH, double bond, no hydrogen bond possible here. When it was open chain, then due to intramolecular hydrogen bond, there you got a new ring which is aromatic, which has aromatic stability due to conjugation. But when it is in ring 1,3-diketone, no intramolecular hydrogen bond between this, no intramolecular cross, no intramolecular orientation will not support to form this hydrogen bond. That's why no additional stability when this 1,3-diketone in ring. Remember it. But when your example is this, one part is ring, one double bond O, take in ring, another take in the exo part of the ring. Here we get the same phenomenon. Like open chain, make a pi bond or participate any one of the keto among these two keto, you will get similar structure like before. See this one hydrogen bond, this one, and it will go to different another canonical form due to extensive conjugation. Here also you will get, and you can draw it. This becomes double bond O, this is double OH. Like previous example, this is aromatic ring, 6 electron conjugated ring. You can match to the structure 1. Here if you take the hexane solvent, also its percentage near about 76%. One double bond I have taken in ring, another double bond in the exo part of the ring, and you got the similar phenomena like open chain pentane 1,3-diketone. Here you got a ring effective due to effective conjugation. It is pseudo aromatic ring like benzene. Now, in the second part of the tautomerism class, I have given so many important examples. How do you will compare different contribution of different enol? Here not due to direct aromatic ring. 1,3-diketone or open chain compound I have explained a pseudo aromatic ring, 6 electron conjugation ring, and that ring formed due to hydrogen bond and OH sigma electron participate in the conjugation, which will make benzene-like ring, and due to that benzene-like ring in hexane, its extra stability, abnormally high percentage got in hexane. This type of comparison of enol form of different keto compounds may will come in different competitive exam, especially in JEE advanced aspirants. Focus on this example and try to digest the explanation. Okay, thank you students. Expecting you got idea about the tautomerism. Now stay with us. We'll discuss different important part of the chemistry with respect to your syllabus. Thank you.